Okay, so this is hopefully the last movie for the midterm review. Um, so page 128, I'm going to tell you right now, we do not need to do B and C here. We're not up to this yet. So wipe this out. So all we're doing is part A on this one. A coffee pot has the shape of a cylinder with radius 5 inches as shown in the figure above. Let H be the depth of the coffee in the pot measured in inches, where H is a function of time T measured in seconds. The volume V in the coffee pot is changing at a rate of negative 5 pi square root of H cubic inches per second. This is a rate of change. So what we want to do is really realize this is dV over dt, and that equals negative 5 pi over, square root of H. And they're saying the volume of the cylinder is V equals pi r squared H. Okay. This is a related rates problem. They want us to show that dH over dt is negative radical H over 5. Well, the volume is pi r squared H. But here's the thing. It's a cylinder. The radius at the top is 5. The radius here is 5. The radius here is 5. The radius is always 5. So that quantity is not changing. So I'm going to actually put that in. R squared would be 25. So V is 25 pi h. Now to get dV over dt involved and dH over dt involved, we want to differentiate both sides of this equation with respect to time. And so we get dV over dt equals 25 pi as a constant times dH over dt. When they were very nice to us, they told us dV over dt was negative 5 pi radical h equals 25 pi dH over dt. And we want to solve for dH over dt. That's what they were asking us for. Divided by 25 pi here, dH over dt is equal to, the pi's cancel, a negative 5 over 25 reduces to negative 1/5. So we get negative radical h over 5 as they wished for. Whoops. As they wished for. That was easy. 29 is not as easy. Whoops. I'm going backwards here. 129. Our famous cone question. A container is in the shape of an open right circular cone as shown in the figure above. The height of the container is 10 and the diameter of the opening is 10 centimeters. Water in the container is evaporating so that its depth h is changing at a constant rate of negative 3/10 centimeters per hour. So when I went through this, I kind of asked you, what do you want? What do you know? Kinds of things like that. So it says, part A says, find the volume V of water in the container when h is equal to 5. Indicate units of measure. This is not a calculus question. This was a warm-up question to help out with part B. So finding the volume V of the water, well, part A says the volume equals 1/3 pi r squared h. And so far, what we know is that height is 5. Well, so now we have the radius and the volume as variables. We need to find the radius. The way to find the radius is to realize this picture has similar triangles in it. And here are similar triangles. Okay? So, what we have is two similar triangles. If the diameter is 10, the radius is 5 at the top. So if I use the red triangle, I could set up a fraction, 5 over 10, so the radius over the height, equals the generic radius and the generic height. That proportion is always going to hold true no matter how far the water level is down in the cone. So when we cross multiply here, what I want to do is get R. Okay? So if you think about what we have here, 5h equals 10R. Divide by 10. R would be 5h over 10, or h over 2. So if the height is 5, then the radius would be, well, 5 over 2, or 2.5. So my volume now is 1/3 pi times the radius, 5 over 2, squared times 5. Which technically you could leave this as the answer. Units of measure would be centimeters cubed, okay? Because that's what happens if you think about it. The radius is measured in centimeters. We're squaring it and then multiplying by a height, which is measured in centimeters. If this is not a satisfying answer to you, we can multiply this out. So you get 5 squared is 25 times another 5 is 125. 2 squared is 4 times 3 is 12. And then have the pi. But on the AP, you could leave the answer unmultiplied out. Now, you may, in Part B, need a nicer answer from Part A, but you might not. All right, so Part B says find the rate of change of the volume of the water in the container with respect to time when H is 5. So we want a rate of change of volume. We want dV over dt. We have the rate of change of the height, I believe. If we look back up at the top, they told us the depth or the height is changing at a constant rate of negative 0.3 centimeters per hour. It's negative because the height's going down because the cone is losing water to evaporation. So this is negative 3/10. So, and we know, and when, we want to find out this rate when the height is 5. So, they told us, we know that V is 1/3 pi r squared h. But if you look, the annoying thing is here we have 2 variables on this side. But armed with this information, we can kill the variable for radius and just have a volume in terms of just height. So we're going to do that. Now our volume formula is solely in terms of height, which is nice because there's one variable, one less variable to deal with. So we have V equals 2 squared is 4 times 3 is 12. So we're going to have 1/12 pi h squared times h is h cubed. So now we have V equals 1/12 pi h cubed. And now to get these rates involved, we're going to take the derivative with respect to time on both sides. So we have dV over dt equals 1/12 pi is a constant, it's going to come along, times the derivative of h cubed, which is 3h squared, it's like a chain rule, dH over dt. So dV over dt is, well, 3/12 reduces to 1/4 pi h squared dH over dt. And now we can plug in our information. We want dV over dt, we have dH over dt, and we have the height. You don't plug in this information until after you take a derivative. That's the biggest common mistake here. So now we know dV over dt is just whatever this is. Technically, you could leave it like this on a part 2 of an AP, but I'll multiply it out just so we get a little more satisfaction of a number here. 5 squared is 25 times negative 3. Well, actually, let's think about it this way. 5 squared is 25. And this is fine. Times negative 3 is negative 75. 4 times 10 is 40 pi. Reducing this fraction, we can divide out by 5. If we divide out by 5, we would get negative 75 divided by 5 is 15. 40 divided by 5 is 8 pi. And we're doing dV over dt, so volume is measured in centimeters cubed. Time is being measured, if I remember correctly, it's being measured in hours. Here's our rate that they gave us. That'll give us the time. Again, be mindful. Indicate units of measure. What happens is if you mess up the units of measure, you'll lose a point on the whole problem. So don't do that. All right, part C. To show that the rate of change of the volume of the water in the container due to evaporation is directly proportional to the exposed surface area of the water. And what is the constant of proportionality? Well, if we take a look at our dV over dt formula, dV over dt, that's the rate of change of the volume. was equal to 1/4 pi h squared dH over dt. We want to show that the volume changing has to do with the area of the water. So we're on a cone. The surface of the water is a circle. The area formula for a circle is pi r squared. So now we want to show that there's a pi r squared hidden in here somewhere. So if we go back to our relationship, we knew that the radius was h over 2. Radius is h over 2. If we want to kill h, because I want to get r, the radius, involved here, I'll go 2r is equal to h, cross multiply. And so dv over dt is 1/4 pi times 2r in parentheses squared dH over dt. 2r quantity squared is 4r squared, so we get 1/4 pi times 4r squared dH over dt. The 4's cancel, and what happens here is kind of neat. This says the rate of change of the volume is equal to pi r squared times the rate of change of the height. In layman's terms, the way the volume changes is related to how much area you have times how much the height is changing. So dV over dt is equal to the area times dH over dt, which was -3 over 10. That was constant. So here is what we have. We have the rate of volume, the rate at which the volume is changing is -3/10 times the area that's exposed. So here is our proof that dV over dt is directly proportional to the area, and the constant of proportionality is just the constant multiplier is -3 over 10. And that's it. Tough, but not terrible if you kind of follow that. All right, page 130. I like this question. This is a nice one. Ship A is traveling due west toward Lighthouse Rock at a speed of 15 kilometers per hour. That's a speed. It's a rate of change. So I'll put that on my diagram here. Now, the ship. This is the trick with this question. The ship is getting closer to Lighthouse Rock. So that x value, which is the distance between, it says let x be the distance between the ship A and Lighthouse Rock. This is decreasing because the ship is getting closer to the lighthouse. So dx over dt needs to be a negative number. Important. Ship B is traveling due north away from Lighthouse Rock. So the y is this guy is increasing as time goes on. So that rate, dy over dt, will be a positive 10. Important. And then it says let y be the distance between ship B and the Lighthouse Rock, which we saw. Part A. Find the distance between ship A and ship B when x is 4 and y is 3. This to me is a killer because it seems so easy that it tricks you, but it's not. It's very simple. You have a right triangle. They told you x was 4 and y was 3, and they want the distance between the two ships. Pythagorean theorem. I mean, if I must do the work here. Here's the work. The distance is 5. That is very, very nice. I think that was probably only 1 point, though. Part B. Harder question. Find the rate of change in kilometers per hour of the distance between the two ships when x equals 4 and y equals 3. I'm going to call the distance between the two ships, which is the hypotenuse of the triangle, I'm going to call it z. Now, as ship A moves in and ship B moves out, that z is changing. It's not always 5. It happens to be 5 when x is 4 and y is 3. But it's not always 5. So I'm going to redo this triangle. All three of these quantities are changing as time goes on. So I cannot plug in a number for any of them. So I will write down the Pythagorean theorem. Now we want to find the rate of change in kilometers per hour of the distance between the two ships. So we want the rate of change of z. So we want dz over dt. And we know that dx over dt was negative 15. Look up top if you're not sure. And dy over dt was 10. And we want to have this happen when x is 4 and y is 3. And that's kind of why they gave you part A. You'll see in a second. So, differentiating with respect to time on both sides, we would get 2x dx over dt, because again, x is a variable that changes as time goes on, so you want the chain rule here, plus 2y dy over dt equals 2z dz over dt. As a matter of algebra, the 2's all can go away. You can divide each side by 2. So x is, now we can plug in the numbers that we know. X is 4. Dx over dt is negative 15. Plus y is 3. Times dy over dt is 10. Equals z, which we actually found in the last problem. At this moment in time, z would have to be 5 times dz over dt. So negative 15 times 4 is negative 60. Plus 3 times 10 is 30. Equals 5 dz over dt. Negative 30 equals 5 dz over dt. Dividing by 5 on both sides. We get dz over dt equals negative 6. And I believe we want units of measure. I'm hoping we want units of measure. Actually, they give you units of measure. Even better. Negative 6 kilometers per hour. You must be negative at that moment in time. If this ship... Sorry, let me do this in colors. The one ship is moving closer. This ship is moving away. But the distance between them, believe it or not, is actually shrinking at that moment by 6 kilometers per hour. All right, part C says, let theta be the angle in the picture, which is the angle between ship A and the lighthouse rock. We want to find the rate of change of theta in radians per hour when x is 4 and y is 3. So when you do this, part C, here's what we know. We have x, y, z, okay? And here's theta. In order to get theta involved, we need a trig function. I'm going to use tangent. Tangent of theta is y over x. And I'm actually going to cross multiply here. I get x tan theta equals y, because the derivatives are a little easier if you use a product rule as opposed to a quotient rule. So now we could take the derivative with respect to time on both sides, remembering that all 3 variables are changing as time goes on. So this first part requires a quotient rule. The derivative to x is dx over dt. The derivative of tan theta is secant squared theta d theta over dt. And we're going to cross these guys. So we get x secant squared theta d theta over dt plus tan theta dx over dt equals dy over dt. Okay, so let's see. We want to do all this stuff. We want to do all this stuff when x is 4 and y is 3. So let's see what we know here. When x is 4, we know x is 4. Duh. We want to find d theta over dt. That's what we wanted. I probably should have written it at the beginning. We want d theta over dt. That's the rate of change of the angle. Plus tan theta dx over dt was negative 15 equals dy over dt was 10. Now, I need to know what secant squared of theta is, and I need to know what tan theta is. Where people get messed up here is, I don't need to know what theta is. I don't need to know the angle. I just need to know the tangent of the angle and the secant of the angle. Here's my angle. I know x at this moment in time was 4, y was 3, and therefore the z was 5. Secant is the reciprocal of cosine. So cosine would be 4 over 5. So secant theta would be the reciprocal of that, which is 5 over 4. Thus, secant squared theta is 25 over 16. That can go right there. Tan theta is opposite over adjacent, which is 3 over 4. That can go right there. Now, this is a little messy, I agree, but life's messy sometimes. So 4 over 16, we got a 4 in the bottom here. So 25 over 4 d theta over dt plus negative 45 over 4 equals 10. If you want to kill the 4's, we can multiply the entire equation by 4. So we get 25 d theta over dt minus 45 equals 40. Now it's easy to solve for. So we get 25 d theta over dt equals 85. Divide by 25. D theta over dt is 85 over 25, which if you divide out by 5, this reduces to 17 over 5 radians per hour. Which makes sense because, think about it, at the beginning, the ship that's moving close is far away and the ship that's moving farther away is close. So our angle is not very large. But as this ship moves in and the other ship moves out, we get a triangle that looks something more like this. So if you think about what happened to that angle, it got much bigger. So the fact that it's growing, the fact that this number is positive makes sense. Whoops. All right, 132. I love this question. I absolutely love this question. Consider the curve given by this equation. Show that dy over dx is that. Implicit diff, we don't have y solve for. I love this question. Here we go. We're going to take the derivative with respect to x on both sides. Derivative with respect to x of x squared is 2x. Derivative with respect to x of 4y squared is 8y dy over dx, or as Alec prefers, y prime, equals the derivative of 7 is 0, and 3x times y requires a product rule. Here are our derivatives. So our derivative would be 3x dy over dx plus 3y. I want to move everything. I want to move all my dy dx's to one side. So I want to move the 3x over. And I will move the negative 2x over to the other side. And I'm doing this because if you look, I want a 3y minus 2x and I want an 8y minus 3x to get our final answer here. So let's see. We would get 8y minus 3x, factoring out the dy over dx. I think you guys can handle all this algebra in one step. Equals, that goes away, and we get 3y minus 2x. Divide by 8y minus 3x. Oops. We get dy over dx is equal to 3y minus 2x over 8y minus 3x. Now, note, you may have done the problem and you get an answer of this. Please understand that this would be equivalent to negative 1 times 3y minus 2x over negative 1 times 8y minus 3x, and the negative ones would cancel. So that's an equivalent answer. This thing is not wrong. You just have to rewrite it how they wanted it. So I showed that this is the case. And the reason why they pose the question like this is the following. If you don't get part A right, part B and C are going to be impossible. So they give you the answer for part A. So if you knew nothing about part A, you go on and do part B as if you have the answer, as if you knew you were doing part A. Part B says, show there is a point, P, with x-coordinate 3, at which the line tangent to the curve is horizontal. And then they're asking you to find the y-coordinate of P. Okay. So if I know the x is 3, I want to show that there's a horizontal tangent. A horizontal tangent means that the derivative, dy over dx, would have to be 0. So let's see what happens here. Well, dy over dx, if x equals 3, would be 3y minus 6 over 8y minus 9. Okay? Now, I would need the y-coordinate of this particular point to demonstrate that this derivative is in fact 0. Well, if they give me an x-coordinate and I want a y-coordinate, I need to go to my original curves equation, which is x squared plus 4y squared equals 7 plus 3xy. I should say this is part B. And if x is 3, then we get 3 squared plus 4y squared equals 7 plus 3 times y. 3 squared is 9 plus 4y squared equals 7 plus 9y. Okay, this is quadratic, so I want to move all the terms over to one side here. And let's see. Actually, you know what? I'm not going to do it this way. I'm sorry. You can do it this way, it's just harder. Here's what we can do, though. What we can do is say, hey, guess what? My derivative has to be equal to 0. So cross multiply. This would mean that 3y minus 6 has to equal 0. 3y is equal to 6. Thus, y is equal to 2. Now, so if x is 3 and the derivative at 3 is 0, then y must be 2. What we have to make sure, though, is that that point, 3, 2, is on the graph of the original function, or the original curve, which was x squared plus 4y squared equals 7 plus 3xy. So we're going to plug in our x and y values and see if, in fact, does the one side equal the other side. 3 squared is 9. 2 squared is 4 times 4 is 16. Does that equal 7 plus, well, 3 times 3 is 9 plus 2 is 18. 9 plus 6 is 25. 7 plus 18 is 25. So yes. So we have now demonstrated that, if you want to write a little sentence to this, a little conclusion, at the point 3, 2, dy over dx equals 0, and 3, 2 is on the graph of, x squared plus 4y squared equals 7 plus 3xy. That's the easier way to do it. You could have done it the way I was going to do it, but you get a quadratic, and I'm not in the mood to do a quadratic. So there we go. So we demonstrated part B that we found the y-coordinate, actually. So they want the y-coordinate. So let's make sure that we under the y-coordinate is y equals 2. Let's make sure we put that in a box so they know that we found it. All right, now part C is interesting. It says find the value of the second derivative at the point P found in part B. So we're going to do that. The first derivative was, of course, the dy over dx was, first derivative was 3y minus 2x over 8y minus 3x. Second derivative says take the derivative of the derivative. And what we do to one side, we must do to the other. So the second derivative would be d2y over dx squared. Quotient rule, have to do it. I know it's annoying. Low d high, so we have high, low. High is 3y minus 2x. Low is 8y minus 3x. High prime is 3 dy dx minus 2, because remember, we're taking the derivative with respect to x. Low prime is 8 dy dx minus 3. This is going to get messy, but if you're keen, it's not so bad. So low 8y minus 3x times d high, which is 3 dy over dx minus 2, minus high d low. High is 3y minus 2x. D low is 8 dy dx minus 3, all over low squared. 8y minus 3x squared. Now, dy over dx is a pain, but if you remember, we are being asked to find the value of the second derivative at this special point, 3, 2. The whole point of 3, 2 was that this first derivative was equal to 0. If we go back to part B's work, so this is actually part C. If we go back to part B's work, the dy dx was equal to 0. So wherever we see dy over dx, it goes away. So this isn't so terrible now. So we get 8y, which is 8 times 2, 16, minus 3 times 3, 9, times 3 times dy dx is 0. So minus 2, minus 3 times y, which is 6, minus 2 times 3, which is 6. Well, that's 0 already, times, who cares, is 0. So this whole term goes to 0. This is really actually not so bad. And then 8y minus 3x, 8y is 16, minus 3 times 2 is, 3 times 3 is 9 squared. So this isn't so bad. So the second derivative at 3 comma 2, 16 minus 9 is 7 times negative 2 is negative 14 over 16 minus 9 is 7 squared, which is 49, which if you wanted to reduce this, you could to negative 2/7. There's your second derivative. Notice that it's negative. That's going to be key in our next part. Next part says, does the curve have a local max, a local min, or neither at this point? Justify your answer. They're giving us the second derivative for a reason. So what we know at this point, these are the things we know at the point. We know at 3 comma 2, we have the following. The first derivative is 0. Second derivative is negative 2/7. Well, the first derivative being 0 tells us we have a horizontal tangent line. Second derivative says, well, if it's negative, says we're concave down. So if we wanted to draw this out, at 3 comma 2, here's what we have going on. A horizontal tangent, and we're concave down at this point. Well, what does that mean? The only thing that can mean is that we have a max, because we know the horizontal tangent has to be there, and we're concave down. So at the point 3 comma 2, the graph has a local max. How do we know this? Because dy over dx equals 0, and the second derivative is less than 0. That's how we know this. I don't even know if they asked us. Did they ask us to explain? I guess they did. You could go even further and say, since we're concave down and we have a horizontal tangent, we know the graph must approach a local max. And you can kind of point to your picture and explain that. Now, we have not covered this thing exactly, but this is something I would expect that you be able to make a connection on the test. And watching the video, obviously. All right, next question. We got a bunch of these. So consider the curve given by y squared equals 2 plus xy. They want us to show that the derivative is y over 2y minus x. So part A, y squared equals 2 plus xy. Taking the derivative with respect to x on both sides. We get 2y dy over dx equals the 2 goes away. X times y is a product rule. So we get x dy over dx plus y. I want to move everything, all my dy over dx's to one side. And now I could factor out 2y minus x times dy over dx equals y. Divide by 2y minus x. And so dy over dx equals y over 2y minus x. Should be a piece of cake. Part B. Find points on the curve where this tangent line to the curve has a slope of a half. Slope of a half, do part B over here. Slope of 1/2, slope equals the derivative. So we want to set this derivative equal to 1/2. So we get 1/2 equals y over 2y minus x. Cross multiply here. This might not be so apparent, but if you do cross multiply here, you get 2y equals 2y minus x. Well, that's a pretty nice nifty little equation, because if you collect your like terms by subtracting 2y, you get 0 equals negative x, which implies that x is 0. That's exciting. So if x is 0, they want us to find the points. They want us to find the y value. So if x is 0, we're going to go back to the original equation and try to find y. Well, the original equation was y squared equals 2 plus xy. Well, y squared equals 2 plus 0 times y, which is just 0. So y squared is 2. Taking the square root and understanding that there are two solutions to this, y is plus or minus radical 2. So there are 2 points. One point is 0 comma radical 2. The other point is 0 comma negative radical 2. Not too shabby. We've definitely done harder ones than this. So part C says, show that there are no points on the curve where the tangent line is horizontal. Tangent line being horizontal, that means the derivative is equal to 0. So let's see what happens when we set the derivative equal to 0. Part C I'll do here. Our derivative was y over 2y minus x. We're setting that equal to 0. Well, cross multiply, you get 0 equals y now. Going back to the original equation, y squared equals 2 plus xy. If y is 0, we get 0 squared, which is 0, equals 2 plus x times 0, which leads you to this equation, 0 equals 2. That equation has no solutions. So, conclusion, there are no values, points, I should say, x, y, such that the tangent line is horizontal. Part D, kind of a weird question if I recall. It says, let x and y be functions of time that are related by that equation. At time t equals 5, the value of y is 3 and dy over dt is 6. Find the value of dx over dt at time t equals 5. It's this kind of bizarre related rates question. So they told us, part D, they told us that x and y are changing as time goes on. So now x and y are functions of time. So we're going to take the derivative with respect to time on both sides and see what happens here. So we get 2y dy over dt this time. The 2 goes away. And now when we do the product rule here, we have to be mindful that x and y are changing as time goes on. So derivative of x is not 1 any longer. It's dx over dt. So we get x dy over dt plus y dx over dt. So here's what we have. Now, let's see what they told us. They told us a few things. They told us time is 5, which doesn't really matter because there's no time in the equation. Y is 3, and dy over dt is 6. So y is 3. We know this. And they would like us to find dx over dt. So we know this stuff. We want dx over dt. So y is 3, so we have 2 times 3 times dy over dt is 6 equals x. Ooh, we don't know x. We do know dy over dt was 6. We do know y, which was 3. And we don't know, well, actually, we don't know dx dt. That's what we want. But we need to figure out what x is. Here we go. If we have y value and want the x value, go back to the original. The original was y squared equals 2 plus xy. So we want when y is 3, we want to find x. Sorry, what 3? Ugh, I messed this up. Don't do that. 3 squared equals 2 plus x, which is what we want to find out, times 3. 9 is equal to 2 plus 3x. It's kind of obnoxious, but 7 equals 3x. So x is 7 thirds. Okay, we can live with that, especially considering the 6 will get rid of it. 2 times 3 times 6 is 36. 6 divided by 3 is 2, so 7 times 2 is 14, plus 3 dx over dt. Subtract 14, we get 22 equals 3 dx over dt. Divide by 3, dx over dt turns out to be no great shakes here. 22 over 3. Final answer. That question to me is kind of, I don't know. I'm not impressed by that question. I don't think that's particularly a great question, but it was an AP question. So, all right, number 134. Doing the same thing here. Showing dy over dx is something. So, part A. You know, I put so many of these on here. It's probably a good idea that you do them, because I kind of like these problems. I especially like, not the last one that we did, but the one before that. I really like that one. So the derivative of x squared is 2x, plus the derivative of 2x is 2, plus the derivative of y to the fourth is 4y cubed dy over dx, plus the derivative of 4y is 4 dy over dx equals 0. I'm going to shove everything over. Sorry, I'm going to shove my non-dy dx's to the other side. So I get 4y cubed plus 4, parentheses, dy over dx equals negative 2x minus 2. Divide by 4y cubed plus 4. And this is not what they have for dy over dx. So we got to do some algebra. If we factor in a negative 2 on the top, we'll be left with x plus 1. If we factor 4 on the bottom, we're left with y cubed plus 1. And negative 2 over 4 reduces to negative 1 over 2. And that's what I believe they had. That's what they had. So dy over dx would be negative parentheses x plus 1 over 2 parentheses y cubed plus 1. There's part A. Part B, write the equation for the line tangent to the curve at negative 2, 1. Lovely. Lovely question. Part B, write the equation of the line tangent to the curve at negative 2, 1. Well, here's my tangent line formula. You should know it by heart. It should be like automatic when you see the equation of a tangent line. Well, they were nice enough and they gave us both x and y. So we know our point was negative 2, 1. So we know y minus 1 equals the slope, x plus 2. Now we need to figure out what the slope is. Well, we're going to turn to the derivative for the slope. So the derivative evaluated at the point negative 2, 1 is equal to the negative value of negative 2 plus 1 over 2 times y cubed, which is 1 cubed, which is 1 plus 1. Negative 2 plus 1 is negative 1. The negative of that is positive 1. Over 2 times 2 is 4. There's your slope. Ta-da! Done. There's part B. Part C, find the coordinates of 2 points on the curve where the tangent line is vertical. A vertical slope is a vertical line rather has an undefined slope. And that's when, say your slope fraction is 4 over 0. The denominator is equal to 0. So that's what we want to do with our slope. Our denominator wants to be 0. So part C, denominator of the slope, the denominator of the derivative has to be set equal to 0. So we get 2 parentheses y cubed plus 1 equals 0. That's good enough as y cubed plus 1 equals 0. That's good as y cubed is negative 1. Taking the cube root of both sides. We do not do plus or minus for a cube root. The cube root of negative 1, what number multiplied by itself 3 times gives you negative 1? Well, that's negative 1. There's our y coordinate. And we want the points, and there's 2 of them. So we got to go back to the original and get an x. Original was, oops, I forgot what the original was. X squared plus 2x plus y to the fourth plus 4y equals 5. Let's see if I can remember that. Original, x squared plus 2x plus 4, no, y to the fourth, right? Y to the fourth plus 4y equals 5. There's our original. So we got to plug in y equals negative 1 and get some x values. So we get x squared plus 2x. Y to the fourth, if y is negative 1, is just 1. 4 times negative 1 is negative 4. Hope we can do that in our heads. So we get x squared plus 2x minus 3 equals 5. This is a quadratic, so move all the terms to one side. We get x squared plus 2x minus 8 is equal to 0. Factoring. we get x and x, positive 4, negative 2. X is negative 4, x is 2. They asked for the 2 points, so we have to write them as points. Our final answers would be negative 4, negative 1, and 2, negative 1. Then part D says, is it possible for the curve to have a horizontal tangent at points where it intersects the x-axis? Okay, if I had any curve, this is not necessarily the curve, but here's a curve. Okay, there's a curve. Intersecting the x-axis, well, what does that mean? It means very simply that if you looked at all these points, the thing they have in common is that their y-coordinate is 0. So they're basically telling us y is equal to 0. We want to see if the derivative, because they said the tangent line should be horizontal at those points, is it possible to have a horizontal tangent? That would mean the derivative is equal to 0. Well, the derivative, if I recall correctly, was negative parentheses x plus 1 over 2 parentheses x cubed plus 1. Well, that's derivative? No, it's not. There's a y in there somewhere, right? Sorry, y cubed plus 1. My memory's getting bad, getting old. All right, so dy over dx is that. Set that thing equal to 0. Well, that's just good as the top being equal to 0. Well, if the top is equal to 0, I could solve for x. The negative 1 doesn't matter. X plus 1 is equal to 0. So x is negative 1. So if, in fact, this curve had a point where the derivative would be equal to 0, where it intersects the x-axis, it would be the point negative 1, comma 0. This would be our candidate, if you will. That's our candidate point. But I don't know whether this point lives on that curve or not. So I'm going to go back to the equation of the curve, which was x squared plus 4y squared. No, I'm lying. I'm doing a different problem in my head. I think it's x squared plus 2x plus y to the 4th plus 4y. So x squared plus 2x plus y to the 4th plus 4y equals 5. And would this point be on the curve? Well, let's see. Negative 1 squared is 1. Plus 2 times negative 1 is negative 2. The y's go away. Does that equal 5? Well, the answer is no. Negative 1 does not equal 5. It's positive 5. Sorry. So the conclusion here is that negative 1, 0 is not on the curve. And there's a couple of different ways to do this, but this is probably the easiest way. So there is no point on the curve that intersects the x-axis and has a horizontal tangent. Impossible. Can't have both at the same time. All right. 2 more to go. I'm getting tired, though. I might stop here, but let's see if I have the strength to carry on. Oh, these are pretty easy. But you know what? Let me see these. 135. Whoops. 136. I mean, we've done this. I'm going to stop here. If you have questions on 135 and 136, to see if you're paying attention, email me or let me know, and I'll do them videos for them. But I don't know if people have gotten up to this yet, so I'm a little concerned. So I want to pause and stop here.